Quantum supremacy is a term used in quantum computing to describe the point at which a quantum computer can perform a specific calculation that a classical computer, the kind of computer we use today, would find impossible or take an unreasonably long time to complete. While regular computers are amazing at many tasks, quantum computers like Sycamore can explore entirely new realms of possibilities, solving puzzles and problems that were once out of reach. Sycamore's capabilities could supercharge RII, making it smarter and faster at learning. Sycamore can solve problems in science, medicine, and engineering that regular computers can't. Think of Sycamore as a superbrain computer built by Google. It doesn't think like a regular computer, but uses something called quantum bits, qubits. Regular computers use bits, which are like light switches. They are either on or off, 1 or 0. Quantum computers, however, use qubits, which can be on, off, or both at the same time. Imagine a spinning coin showing heads and tails simultaneously. In October 2024, Google's Sycamore processor, a 67-qubit quantum computer, achieved a significant milestone in quantum computing by operating in a weak noise phase. This advancement enabled it to perform computations that are currently beyond the reach of classical supercomputers.
Scientific explanation. Quantum supremacy marks the point where quantum computers can solve a problem that classical computers cannot achieve within a reasonable time frame, even using the best available supercomputers. Google's Sycamore processor demonstrated this by performing a random circuit sampling task in 200 seconds, which would have taken Summit, a leading classical supercomputer, approximately 10,000 years. The breakthrough illustrates the unique computational advantages of quantum mechanics, where operations rely on principles such as superposition and entanglement. Example: the random circuit sampling problem involves generating a series of outputs based on the complex interactions of quantum states, which classical computers cannot efficiently simulate due to the exponential growth of possibilities. Analogy: quantum supremacy is like discovering a new form of transportation that travels a path impossible for conventional vehicles. The journey may not yet have practical applications, but it proves that the new mode of transport, quantum computing, can overcome obstacles that traditional ones cannot. Scientific explanation. The Sycamore processor contains 54 superconducting qubits, though only 53 were functional during the experiment. Superconducting qubits operate at cryogenic temperatures to eliminate electrical resistance and reduce environmental noise. The two-dimensional grid layout of qubits enables effective nearest neighbor interactions, critical for implementing 2-qubit gates efficiently. These gates form the building blocks for complex quantum algorithms. Example: the qubits in Sycamore can simultaneously represent and manipulate data in 254 states, compared to binary bits in classical systems, which represent only one state at a time. Analogy: think of Sycamore as a choir with 54 singers, where instead of each singer producing a note sequentially, the entire choir produces a harmonious blend of all possible notes simultaneously, creating an exponentially richer performance. Scientific explanation. Random circuit sampling serves as a stress test for quantum processors, evaluating their ability to produce random outputs from a quantum circuit. The complexity arises from the need to simulate quantum entanglement and interference patterns, which grow exponentially with the number of qubits and depth of the circuit. Classical computers face memory and computational constraints in handling these tasks. Example: Sycamore implemented circuits with over 1,000 gates and achieved sampling fidelity of about 0.2%, demonstrating accurate quantum state preparation and measurement. Quantum coherence refers to the ability of qubits to maintain their quantum state without decoherence caused by environmental interactions. Sycamore employs advanced error mitigation strategies, including error-correcting codes and precise calibration of qubit operations to minimize disruptions. Each quantum gate operation introduces slight inaccuracies, and managing these is critical to scaling quantum systems. The fidelity of Sycamore's 2-qubit gates was 99.4%, meaning errors occurred in fewer than 6 out of 1,000 operations, a significant achievement for superconducting qubits. Maintaining coherence is like trying to balance a spinning top on a shaky surface. It requires constant, precise adjustments to keep it stable and prevent it from falling. Quantum gates are operations that manipulate qubit states through specific unitary transformations. The speed and accuracy of gate operations determine the overall performance of a quantum processor. Sycamore achieved a gate operation time of approximately 25 nanoseconds for single-qubit gates and slightly longer for 2-qubit gates. Consider a 2-qubit gate like the controlled NOT, C0, which flips the state of one qubit based on the state of another. Such gates are essential for creating entanglement, a cornerstone of quantum. Scaling quantum computers from tens to thousands of qubits requires addressing issues such as qubit connectivity, noise, and error rates. Current superconducting qubit technology faces physical limitations, such as the need for ultra-low temperatures and shielding from external electromagnetic interference. Doubling the number of qubits exponentially increases the computational possibilities, but also introduces more potential points of failure, requiring robust error correction. Scaling a quantum computer is like building a suspension bridge. Every additional cable improves strength but also increases complexity and the risk of failure in one weak link. Shor's algorithm, when implemented on a sufficiently large quantum computer, could factorize large integers exponentially faster than classical methods, rendering classical encryption like RSA vulnerable. While Sycamore demonstrated quantum supremacy in a specific task, practical quantum cryptographic applications remain years away due to hardware limitations. A 2048-bit RSA encryption key, which would take classical computers billions of years to break, could theoretically be compromised by a large-scale quantum computer in hours. Classical cryptography is like a medieval fortress with thick walls and heavy gates. A quantum computer would be akin to a tunnel-boring machine that bypasses the defenses entirely. The broader goal of quantum computing is to solve problems intractable for classical computers, including simulating quantum systems, solving complex optimization problems, and enhancing machine learning. Sycamore's achievement highlights the potential to model molecular interactions for drug discovery or optimize supply chains. Simulating the quantum interactions in a caffeine molecule is nearly impossible for classical systems due to the sheer number of electrons and interactions involved. Quantum computers could make such simulations feasible. Classical computing is like a candle illuminating a small room, while quantum computing has the potential to light up an entire city with its expansive problem-solving capabilities. Sycamore represents a proof of concept rather than a practical tool. The next steps involve developing error-corrected, fault-tolerant quantum systems and integrating quantum computing into hybrid classical quantum workflows for enhanced performance. Efforts are also focused on discovering new quantum algorithms tailored to real-world applications. IBM and Microsoft are exploring quantum cloud platforms to allow researchers to test algorithms on quantum processors, bridging the gap between experimental and practical use cases. If Sycamore is the equivalent of the first electric car prototype, future quantum systems aim to be like fully autonomous electric fleets, revolutionizing industries and reshaping computational paradigms.